Okay, so my plan for today is to like finish discussing the topics for the first exam. So again, I think I sent like a study guide over the weekend, so check that one out. And I will post solutions to like these uh problems on the PDF, uh probably like around Thursday, so that to most of them at least, so that you have like time to submit the solution. I think there was still like some assignments that were due this week. So like just do the submission for that, and then like I'll kind of post the solutions to like the PDF problems after that, after the deadline. But like the exam will be again, like there's still not much that we have covered, like in terms of like topics, like I can kind of like put it here. So there's like the word problems, right? Where like, I write like, oh, like you're like a store, like you're trying to sell this, blah, 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 right? Like a optimization model that maximizes the profit. So like, but for that, I just want you to set it up. Like I wouldn't like ask you to solve it because again, we still haven't talked about the simplex method to solve things, but just like the setup. I do probably will ask something like that you solve graphically, but then that would be something like that you can draw on the XY plane, because like then you can find the corners and like do this thing. So like an optimization solved with the graphical method. But yeah, that would only have two variables because that's the only thing you can realistically graph, uh, which is solved graphically. So I believe like on the previous assignment, like what like this thing about the bags, like the sleeping bags, or like we have done some of those, like the carrots and the potatoes, like like that's where you draw like all the constraints on the plane and you get like the polyhedra and whatever, and then you check for the corners. Then another thing which is like important is to turn like the inequalities into equalities by adding extra variables. That's also like important thing to keep an eye on, turning inequalities into equalities. And I don't think I'm like so. And then like finding basic solutions. Problems about like if something is convex or not, convex or not. I mean, there's not. I don't want to. If you have to say that something is convex, it would just be by picture. And if something is not convex, you would give 2 points whose line segment is not in the set. So it's more like more. It would be mostly visual those, but it's still kind of like nice to like it's still convexity is an important thing. So like um and then this basic solution stuff. So finding some, which is what we're still discussing, and degenerate basic solutions also, which I'll tell you about today, which is like a nice an important concept as well. So in terms of topics, like one, two, three, four, five, six. So like there are about six things. So like, I mean, some of these is like they're shorter than others, like turning like a system of inequalities into equalities. That's very algebraic, so it's kind of like a mini problem. But like so, but those are kind of like the six main topics we have discussed so far. Well, the last two I still have to tell you more about today, and then well, yeah, I don't know, like, based on the weather apps, like, some tell me that there will be snow on Wednesday, and others tell me that there won't be any snow. So I don't know what the situation is like, but if for whatever reason, like, they ask us to move all the classes online, then I'll just send you an announcement tomorrow evening, just letting you know that, the classes would be online, for Wednesday. But I'm again, we just wait until what happens there. Uh, but if I haven't said anything by Tuesday evening, then that means we're still meeting in person, because they wouldn't ask us to move online on the same day. So, okay, so just to go back, oh yes. The exam would be next Monday. Yeah, right, next Monday during class time. Yeah, yeah, yeah. And something like the inverse for a 2 by 2 matrix, that's a formula I would write on the exam so that you don't have to, like, if needed, like for this basic solution stuff, that can be a useful formula to have around. So I would just like write the formula for the inverse, like so that you don't have to worry about like finding it. Yeah.
Is basic solution degenerate basic solution what we're doing today?
Yeah, well, the basic solutions we started last time, but yeah, like the degeneracy, I still haven't said anything. Uh, Basic solutions are kind of like midway. Like I already said most of what I wanted to say about them, but I do want to do like a more thorough example where like you see everything in more detail. And then the degeneracy is like it's like a small thing, but it's kind of like a important thing to also know. Um, okay, so yeah, like actually back to basic solutions, which is what I want to focus on today. Again, just to usual setup, we are trying to find the max or min of a dot product, and the constraints are that, like all the variables are non-negative, and we assume already that we put the system into equation form, so there are no inequalities. So like the you have a matrix, you have a bunch of equations that like the variables need to satisfy linear equations, which again, if it's in inequality version, then you had to add like this like slack variables or whatever to turn them like the inequalities into equalities. Now, um, the basic solutions, the basic solutions have they just have to do with ax equals b. So the basic solutions are found using only. So nothing else about the problem is relevant to this basic solution stuff. You don't care about what you're maximizing or minimizing. That has nothing to do with that. But well, I mean that's and whether they're like the variables are positive or negative, that plays a role later. But like when I ask to find basic solutions, like that's not something exclusively about the system of equations. Okay, so what I was explaining last time is that in the context of the matrix that we have, remember, A is a rectangular matrix with which has more columns and rows, right? With more columns and rows. And then to find a basic solution, well, first you find a basis for the matrix, right? So you find a basis first. And what was a basis? A basis was just like a square matrix, right? From built from A, which is invertible. So it's like a square matrix built from the columns of A. Okay, actually, where do I have this? Okay. And um, so let's call that step one. Okay. And so for today, basically what I'll do is kind of like at least for like the first half, I think I'll work out in extreme detail, like an example which will kind of like illustrate everything that's going on. So um and again, this will be kind of like our main example for today. Everything will be extracted out of it. Okay. So I'll give you this matrix A, which will be 1/8, 1, 0, 0. Then 1, 1, 0, 1, 0. Then 2, 0, 0, 0, 1. Okay, so what is this matrix? This is a 3 by 5, right? So this is a 3 by 5 matrix. Right? So if I were to say, oh, find all the possible bases for this matrix, right? So find all the bases for A. Right? What that means is like I'm trying to find like because this has 3 rows, like any square matrix that I built, I want to make 3 by 3 matrices, square matrices out of like the columns of A. So I want to build 3 by 3 matrices from the columns of A, which are invertible. Okay. So I don't know if you remember last time, I actually kind of so basically we have 5 columns, right? I have to choose 3 from those 5 columns. I don't know if you remember, like there is like an estimate that you can make for what's the most that you have to look for, right? Which was this combinatorial symbol, which is called like n chooses k. So it is good to know when to stop, right? What is the maximum number like of like groups of matrices that you have to look at. So in principle, you need to consider 5 chooses 3, which is 5 factorial, divided by 3 factorial times 5 minus 3 factorial. So that's 5 factorial over 3 factorial divided by 2 factorial. And then 5 factorial is 5 times 4 times 3 factorial divided by 3 factorial times 2 factorial. And like the 3 factorials cancel and 2 factorial is just 2. So you get 5 times 2, which is 10. Okay, so basically what this is saying is that from 5 columns, you can select 3 at there are 10 ways to select 3 at a time if you don't care about like swapping like choices. Yeah.
It's 3 by 3 because there's 3 rows.
Correct, right. So if it had been like a 4 by 5 matrix, then you would have to look for 4 by 4 matrices. Yeah. Correct. Good.
So first we should probably check that all the columns are linearly independent, right? And then we can choose like,
Well, the thing is like all the columns cannot be linearly independent because the rank, right? Like the rank of this matrix, like if I think about it this way, these columns have 3 entries, right? So they all live in R3. R3 has dimension 3. So if they were all linearly independent, they would be like a basis with 5 basis vectors for R3, and but R3 having dimension 3, the most it can have is like 3 vectors which are linearly independent. So like at a time, only 3 of these 5 columns can be linearly independent, in fact.
yeah, but like, what if we choose like 2 columns and then the third column's like a linear combination?
Oh, then that
Then
one.
how wouldn't that be included in the 10 ways?
Yes, exactly. This is included. So the 10 ways include everything, the
Yeah.
ones that work and don't work, right?
Oh.
But that is right. So in fact, one of these won't work. You'll see it in a second. So what I'm saying is kind of like this is the most, like, this is the maximum number of matrices you have to check, but some of those won't work, right?
Yeah.
And in fact, okay, perfect. No, like this is also good. So now we do have to, I'll kind of like take advantage of the fact that I can just copy paste on the iPad because, okay, let me teach you what's the, and this is kind of like a bit of combinatorics, but it is kind of like nice to write this in a way that's kind of like somewhat organized. So you want to choose, like, columns are column 1, column 2, column 3, column 4, column 5. So just imagine selecting 3 numbers at a time of 5 numbers, right? So like this is like a nice way to do it. Like, so one selection could be 1, 2, 3. I'm kind of going to write them in like an order, like arrangement. So 1, 2, 3 is kind of like column 1, column 2, column 3. Then I'll keep 1 and 2 first, and I will just kind of change the last one. So like I would put up 1 to 4, right? And then I could also put 1 to 5. Okay. So and again, I'll kind of like I'll draw like the matrices in a moment that corresponds to each of them. I just want to go first through all the 10 possibilities so that you see them. Okay. So these are the first 3. Then the next ones, they can still start with 1, but I'll put like a 3 in the middle. So I'll do 1, 3, and 4. Okay. Then I'll do 1, 3, and 5. Okay. Is there another one that I'm like missing that it could start with 1 that you can see? What am I not? Is there one left that starts with 1? What do you think? Yeah. Yeah, 1, 4, 5. And it really helps to know that you have to go to 10 because it's easy sometimes to miss them, like, So perfect. 1, 4, 5. And I cannot continue, right? Because I cannot do 1, 5, because if I do 1, 5, there's nothing else to put left, right? So perfect. So that already gives us 6 of the 10 candidates, only 4 more to find, right? So oops. And now where is my okay? So I'll try to fit the last 4 here. So I'll put 2, 3, 4. That's a possibility, right? Because now I cannot start with 1, so I have like the next number to start with is 2. Then I could do what? 2, 3, 5, right? Then I could do 2, 4, 5, right? And last but not least, I could do what 3, 4, 5. And then 3 plus 3 plus 4 is 10. And it's good to know the combinatorial value for the choose escape, because that tells you you don't have to worry anymore. Like that's the most like you could have found, right? Yeah.
I know that this is a topic that's gonna be on the exam, but it's a little bit time consuming to have to check all the matrices or all the different combinations for the basis. Is there a faster way to?
Well, not at the moment, but it would just be like a smaller matrix.
Oh,
Yeah, or like for not, it doesn't have to be like necessarily like a smaller matrix. Wait, like so for example, even if I had done like like a 4 by 5 matrix, right? Then it would have been 5 chooses 4, and 5 chooses 4, I guess it's 5. So it would have been like 5 options instead of 10, So it doesn't, even like ironically making the matrix bigger can actually reduce the number of things you have to check, if you know what I mean. So, but yeah, like it would not be like, I mean, it would be something where like it's realistic to check in practice. But I do think it's kind of valuable to kind of like go through like something with all the possibilities so that you see like kind of like what happens, like like, but right, like the point of the simplex method is to kind of like avoid having to kind of go through like the entire listing, but it's kind of like useful to know, okay, which are all the possibilities, like in a comprehensive example. But yeah, I would give something where like like maybe it's like 3 or 4 things that you have to check, nothing like too long, so because yeah, even if I had to write this like without like the iPad, like it would take me like an eternity to do so. So let me, sorry about that. Oops. Which is not like, well, this is not an advantage you have at the moment that well, unless you have like an iPad that you're working with. Um, of course, I still have to delete, but I'm just doing the copy pasting first to. Okay. Okay. Let's leave that like this. Okay. So those are like the 10 possibilities. And again, you would like eliminate the rows and columns that you don't care about. So here I'm just only keeping track, keep the first three. So I delete the last two. So let me delete the last two here. Then here, what do I have to delete? I have to delete 3 and 5 for the next one, right? I just keep one, or better to think about what you're keeping. You're keeping 1 to 4. Then here you're keeping 1 to 5, so you're deleting 3 and 4. Okay. And it's kind of like nice to do it this way because you kind of see how like it's kind of like emptying out, like removing some of the columns and while keeping the other ones. And then 1, 3, 4. So like you remove 2, remove 5, then 1, 3, 5. So you remove 2 and 4. Okay. Then 1, 4, 5, you remove what? You remove 2 and 3, right? Then now you remove the one you remove 1 and 5. Then 2, 3, 5, you remove 1 and 4. And then like this is 1 and 3, right? And then what? 1 and 2, right? Is that okay? Is that making sense? Okay. And again, of these 10 possibilities, some of those will give you a basis and others won't. Those with determinant not zero will give you a basis. Those which with determinant zero do not give you a basis. So of course, again, like in practice, like I wouldn't expect you to check this for so many matrices. We're just doing this right now because like a more thorough example kind of like shows you what's going on. But here, like, if you remember certain properties of the determinant, they're not that bad to compute because there's a bunch of zeros in most of them. So for example, like if you remember, like the determinant can be expanded along any row or column. So for example, if you take column 3, delete column 3, row, like, if you delete the the row and column to which this belongs, you just have to find this determinant and you see that it's not zero. So like, I'm just saying like for most of them, if you kind of like choose the appropriate row or column, actually it's like 2 seconds to check whether the determinant is zero or not. So here, so I'll just put like this is like this one will be invertible. This one is also invertible. Like the only one that is not invertible is I don't know if you see it. Um, it's like this one because it has like a row full of zeros. So because this one has a row full of zeros, like that one won't be invertible. All the others, if you play with the determinant, you'll find that it is not zero. And again, like you just use like the properties to kind of like check. And I'll use a different color for this one, so not invertible. Is that making sense? So far, so good. Questions up to this point. Okay, so of the 10 potential choices, 9 of the 10 define what you would call like a basis for the matrix. So of the 10 possibilities, mhm.
The 1, 3, 5 is invertible.
Let's see, 1, 3, 5. Let's see. So uh if I use this column, right? So yeah, you just have to, yeah. No, like please. So I mean, like it is like it took me I was doing it on the train today. So like it does take a while to like do carefully everything, like make sure like I mean because like but I'm just saying like you choose like the one with most zeros and so that it hopefully you just have to do a 2 by 2 determinant, like So of the 10 possibilities, 9 are define a basis, 9 choices define a basis, and only 2, 3, 4 does not. Only choice 2, 3, 4 does not. Okay, so far so good. Questions up to this point? Okay, and now and here comes the crucial part. What's the point of doing this? That once you have a basis, what I'm saying is that I can produce a solution to the system of equations. Okay, so like that's step 2. Once you have a basis, you can find a solution to AX equals B. Okay, and again, I kind of went over it last time, but I'll kind of mention it again. So how do you find the solution? Like the idea is to you solve first. Okay, so you solve first AB equals times X equals B. So what does like this mean? Like this meant like this is like the matrix that you get corresponding to the choice of basis. Okay, let's call the basis B. So this is like the matrix, like the square matrix determined by the basis. Okay. And let's call this X sub B. And these are like the variables, again, also determined by the basis. And I'll kind of explain what I mean by that. So like this is like the and here this is like the vector of variables determined by the basis. Okay, so let's like I'll do it for one of like the 9, one of the 9 that is not like obvious, immediately obvious. So for example, let me choose one that it doesn't take too much time. Okay, let's say which one do I like about of this one? Okay, I'll do it for 145. Okay. So here's like an illustration for how this method works for 145. I'll kind of rewrite it in a moment. I just want to do it like kind of write it. Illustration for the basis, which is 145. So if the basis is 145, oh, by the way, I didn't, sorry, did I write this? Okay, like the example for today is a matrix, but I do need like a vector B. I had not written it before. So I'll put the vector B to be, like, let me check what I had used in my notes. I think it was 42432 or something like that. I mean, like the basis is determined only in terms of the matrix, but to find the solution, you do need to use the vector B. So 423, yeah, sorry. Okay. Okay, so oops, like I shouldn't have erased it so far. So if the basis is determined by 1, 4, and 5, then the corresponding matrix is what I would call A sub B. So it's just like this one that you see here, 1, 1, 1, 2, 0, 1, 0, 0, 0, 1. Okay. And what is x sub b? That's also important to understand. These are the variables that are selected by the basis. What are the variables selected by the basis? 1, 4, and 5. Yeah.
Is the B vector given to us?
Oh yeah, like the b vector would also be given to you. Yes, yeah. I mean the matrix and the vector would have to, unless like like they would be given basically. Because this part does depend on what b you were given. Yeah. So what oh sorry, I shouldn't have called them 1, 4, 5. Like what I'm trying to say is that since the choices were columns 1, 4, and 5, the variables corresponding to those columns are x1, x4, x5. So those are the ones that would be assembled in this vector. So far, so good. So the system of equations would be this one, the matrix times this vector equals the vector b. Oops, so what happened here? Let me see. Did I touch something? Oh, let's go back. Went back to life. So what we're trying to solve is 1, 0, 0, 1, 1, 0, 2, 0, 1 times x1, x4, x5 equals 1, 4, 5. Is that okay? Okay. In most cases, like like again, for these examples, either you solve the system directly, like row reduce it, or like sometimes like there's enough zeros that it's kind of like more direct what is going to happen. Because if you, for example, if you do this matrix multiplication, you get what? You get x1 this is what you would call like lower triangular. Yeah. Oh yeah, thank you. Like, oh my God, thanks so much. Like you saved it. So what was a v vector? Just yeah, thank you. Yeah, that's a good like yeah, I think glad that you caught that. 4, 2, 3. Yeah, you do. Yeah. Correct. So what I was saying is that, most of these matrices have bunch of zeros. So in fact, this one is, I think this was called lower triangular. So when they're like triangular, it's super easy to solve like the system of equations. If not, you kind of row reduce, like, but again, like we are kind of going to deal with very small cases where like, it wouldn't be super long what we're doing. Okay, but if you do like this matrix times this vector, that's the vector that you find. So that gives you 4, 2, 3. Okay, and like, so it gives you what? Like the first equation says, the first entry of the vector says, say that x1 equals 4. Then x1 plus x4 had to be 2, right? So that would immediately say that 4 plus x4 had to be 2. So that gives you that x4 has to be -2, right? And then 2x1 plus 5 plus x5 had to be 3. And then that gives you what? That 2 times 4, that's 8, plus x5 equals 3. And so that gives you that x5 equals -5. Okay. So in this case, like the vector x1, sorry, the vector what I'm calling xb would be x1 what, right, x4, x5, and we just found that that would be 4, -2, -5. Is that okay? Is that making sense? So far, so good? Up to this point, questions? So, okay, and then the solution to the system, like, the vector, like the vector we started with, like there were 5 columns, so there were 5 variables, right? Like I kept the 3 chosen by the basis. So the solution to the original system of equations is just found by adding zeros to like the remaining spots. So like what am I missing here? 2 and 3. So I put like a 0 and 2 and a 0 in 3. So like, finding the solution is very easy. You just fill it out with zeros. So to find the solution to like, and then the solution x to AX equals B is, you know, uh,
Professor, that
Hmm?
like couldn't be negative.
well, uh, it won't be feasible, but it is a solution. It's just that it wouldn't satisfy the constraint. Yes, we're still not worried about that part. Once we look with whether all the entries are negative, positive or not, that is called feasible. Feasible. So this is still like a solution. Like right now, I'm just talking. How do you find a particular solution to the system of equations? And this does solve the equations. It's just that it wouldn't satisfy the extra constraint that all the variables are non-negative. Right, right. And then you would call, so this will be called like an infeasible solution. Like, yeah. Yeah, but that's a good, like, that's like a good observation. So obtained by adding set, by putting zeros for the remaining variables, which are called non-basic variables. Like, not like too surprising of a name, maybe zeros to the remaining variables. So in this case, like our solution for this basis, so for the basis 1, 4, 5, the basic solution, sorry, like the actual solution, like not just like the basic part, is like, okay, put 4, 0, 0, -2, -5. And this solves, and this one solves, and this one solves like the system of equations. Okay. That makes sense. Questions about? Okay, and now it comes to your point that, right, as a remark, so this is, this is a solution, right? So like a remark, notice that that this vector, right, does not satisfy the constraint that like that the vector has to be non-negative, right? Because some of its entries are negative, right? Because because it has negative entries. Okay. Okay. So because it has negative entries, it's called like an infeasible basic solution. So it's called, so we call this an infeasible basic solution. Because it is a solution, right? It is a solution. It is basic because it's associated to a basis, but it's infeasible because that is not what we're after, because we are after vectors whose entries are non-negative. Okay, so the word feasible, when you say that something is feasible, that means that it satisfies all the inequalities or all the constraints, everything in the system. And if it's infeasible, is that it fails to satisfy something. Okay, so actually what we do want is like the feasible solutions, like those are the ones that we actually care about. Okay. Yeah.
So like, when you give us like a basic solution problem, are you gonna give us constraints and then we check to see if the basic, like the solution satisfies those constraints?
Well, I mean, the thing is like, it depends, like, the constraints, like, the constraints in all these optimization problems only come in two types. Like the first constraint is that all the variables are non-negative, and the other is that it satisfies the equation, right? So the point of the basis is that it takes care of this part. The only thing that may be left is that some may come out with negative entries, right? So, but that is like a constraint that is easy to check because it's just like you just scan like entry by entry, right? But all the other constraints are kind of like like assembled into the matrix. And that is kind of like by guarantee from the fact that you found the basis.
Sounds good, thank you.
So just to continue, what I'll do, like I'll do one of these where like you do find like a basic feasible solution, and then I'll give you the list of all the ones that work because something fun happens here. Okay. So let's see. And again, like this, like actually, right. Let's do 1, 3, 4. And then I'll just give you like the list of all the ones that work. Another basis. 1, 3, and 4. Okay, so if you do 1, 3, and 4, oops, sorry about that. If you do 1, 3, and 4, then the matrix associated to this matrix we had already found. So it was 1, 1, 2, 1, 0, 0, 0, 1, 0, right? Then the vector of variables, right, are the variables corresponding to those positions, right? So it would be what? X1, X3, X4, right? And B is still like, yeah, B is always fixed. It's 4, 2, 3. That does not change. Like, that's kind of like the same for all the problems. So now what we have to solve is 1, 1, 0, 1, 0, 1, 2, 0, 0 times X1, X3, X4 equals 4, 2, 3. Okay. So you get X1 plus X3, then you get X1 plus X4, and then you get 2X1. That has to be 4, 2, and 3. And again, like you see, like these systems are not that bad to solve in practice because like if you start with the last equation, right, or the last entry, so you get that X1 plus X3 equals 4, that X1 plus X4 equals 2, the 2X1 equals 3. So, the last entry says that X1 equals 3 halves, right? And once you have that, X4 is 2 minus 3 halves. So 2 minus 3 halves, that is 4 minus, that's just 1 half, if not mistaken. And then this one would be 4 minus 3 halves, which is 8 minus 3 is 5 halves. Okay. So in this case, the basic variables, what are the basic variables? They were X1, X3, X4, right? Which would give you, X1 was 3 halves, then X3 was 5 halves, and then X4 was 1 half. Oops, sorry about that. Like I always forget to go down. Is that making sense? And then what is the actual solution? Like the solution vector is just that one, exact same one, but putting zeros in the remaining spots, right? So the solution vector itself, it would be x1, x2, x3, x4, x5, right? But you said equal to 0, the ones that you didn't use. So like the positions 2 and the positions like 2 and 5 were set equal to 0, and then the others are fine. Is that okay? Is that making sense? So far, so good. And okay, so this is great. This satisfies the system of equations. Okay, so this vector solves ax equals b, which makes it a basic solution, right? So it is a basic solution. It is a basic solution. But in addition, now every entry, right? Every entry is non-negative. So it satisfies the other constraint that like all the entries. So it is uh, basic, like a feasible basic solution. So you call it feasible whenever everything is satisfied, like solve the system of equations and it's non-negative, everything. Okay. Questions so far so good?
So it's only basic because it satisfies AX.
Right. You use the name basic if it is exclusively related to the equation, because that only depends on the basis. And you add the word like, or what, like the adjective, I guess, feasible, if it, in addition to that, it happens to satisfy the second, like the constraints about like the non-negativity. So, and like hopefully the kind of, and every single problem would be done this way. Like, of course, like again, like the idea is like we'll have like a more efficient way to do this in a moment, like next time or like maybe after the exam. But the idea is that so the goal is to find the basic feasible solutions. Like, so just to like find the basic feasible solutions, since those correspond to the corners of the region. So since these correspond to the corners of the region, which is where the max or min could occur, which is and in fact, okay, like it is not worth, I don't think at this moment to kind of like go through why that is true, that like a basic feasible solution gives you a corner. It's not super complicated either, so I'll just write down like a note for it. And if you want to read it, then you can read it. It is like a very clever proof. It's actually very nice, but going through it right now is kind of like, you know, a bit of like a detour. And it's kind of like one of those things that you have to sit down, like go through the proof, like every single line and make sure that every step makes sense. So I kind of like will write a proof and send it to you of why a basic solution gives you like a corner. It's like a very clever thing. Like it is like like if you appreciate proofs, it's like a very beautiful proof, but it's not kind of like the point of like what we're trying to do right now. So I'll send you a proof of this. But in fact, just to kind of like, at least but just to kind of wrap up this example, let me tell you what all the basic feasible solutions are. So we've found one, and if you went through, like again, sorry, just to kind of like go back for a second. We started with 10 options, right? We dropped one because it was not invertible. And of these, when you start finding the vectors, some will have negative entries, right? So you would drop those as well. So at the end, if you went through the entire, like if you were to do what I was doing earlier for every single possibility, you would find that there are 5 vectors that's solved, which are basic and are feasible. So in our example, and I'll just give you what those vectors are. So because I'll use them in a second to illustrate this point. Our example, you find that there are 5 basic feasible solutions. So the let me see if I can write them all. So I'll put here like what were the columns that this like was associated to. So like the 5 ones are like these 1, 2, 3 does produce a basic feasible solution. It would have given you this. Then where is the second one? 1 to 5. Like columns 1 to 5 also produce a basic feasible solution. And by the way, I use Wolfram Alpha to do this, like to do all the systems of equations. I wouldn't, because yeah, this is kind of like an example that like would take a lot of time to do in practice. But if it's kind of something where you just have to check for bases or whatever, like then that's kind of like within grasp. But like it doesn't take that much time. But like you just have to be somewhat patient. So this is the first one. This is the second one. Then the third one was associated to columns 1, 3, and 4. Okay. Which is gives you 3 halves, 0, 5 halves, 1 half, 0. And then where is the fourth? The fourth one is associated to 2, 4, 5. Which gives you, fourth one gives you 0, 3 halves, 0, 1 half, 3. And the fifth basic feasible solution gives you what's associated to 3, 4, and 5. And that gives you 0, 0, 4, 2, 3. Okay. So what that means is that in this region, the region, like the convex set, had like 5 corners. So like whatever the convex set is, it has 5 corners. So the convex set we were working with, like corresponding to has 5 corners. Okay. Is that okay? Is that making sense? And just to illustrate this, because this is kind of like nice to see with like an actual picture. So let me show you like this. Of course, like I cannot show you this directly, right? Because, okay, what is the problem here? I cannot show you this directly because if you go back, I mean, the system had like 5 variables, right? So like the picture involves something in 5 dimensions. So I cannot show like the picture in 5D to show you like the 5 corners. But what I can do, like just to illustrate this for you, so like imagine let's see. Okay. So imagine if I had started with like like a region on the plane, right? Okay, this is like actually pretty cool. So let's see. Actually, let me see if I can, I'll draw sorry about that. I'll draw the inequalities on the board so that you can keep track of them. Okay, so if I ask you, oh, use the graphical method to like show how this region looks like, okay? So, oops, like, let's see. You know, how do you show, like, how do you find this like graphically? First, what you kind of like plot is each equality, right? So for example, you put like, well, 8/3 is like 2.67 roughly, like, which is what, oops, like every time I kind of touch the computer, like the static electricity, it does that. So, this in like that corresponds to the, like when you set the first inequality to an equality, and then the x plus y equals 2 would give you this line, and then 2x equals 3 gives you this line. Okay, so those are like the three where is my mouse? Okay, those are the three inequalities turned into equalities, right? But because it's less or equal to, you kind of have to look at all the points that are satisfying the three inequalities at once, together with being in the first quadrant, because like the two variables have to be non-negative, and so the polyhedra or the polygon that you get is this one. Okay, and if you kind of look at it, this has how many corners? It has one. Wait, let's see. 2, 3, 4, and 5 corners, right? So this polyhedron has like 5 corners. Okay, and how is this related to the problem that we were doing like a few moments ago? Because otherwise I wouldn't bring it up. Because if you, just to go back to like, where am I? Here. I'm sorry, via cable. If you do it, if you kind of like rewrite this equation into the standard format, rewrite in the in the equation version, right? What does that mean? It meant that you had to add like a slack variable for each inequality. So you would get x1 plus 8/3 x2 plus x3 equals 4. And then x1 plus x2 plus x4 equals 2, right? And then 2x1 plus x5 equals 3. Then you would get the following matrix. You get 1, 8/3, 1, 0, 0. You would get 1, 1, 0, 1, 0. And then you would get 2, 0, 0, 0, 1. Okay. And hopefully that matrix looks familiar, because that is literally the matrix. Where are you? That is a matrix we have been working all this time along. So essentially, like the idea is that so like this is like the same matrix as from before. Matrix from before. Which had 5 basic feasible solutions. And 5 basic feasible solutions. Okay. Yeah.
How did you get those three?
Oh no, I mean, I kind of like, I kind of start like I went backwards. I started with that I wrote those inequalities. I found the matrix.
Oh, so you were going back.
Right. Yeah. I got like, that's how I set up like the example. But what is kind of cool to see is like, if you were to draw this on the plane, right, you do see like the corners very clearly, right? And if you kind of do the matrix trick, to set it into equation form, like you find the 5 corners. The only thing, like, that doesn't matter too much to go into details here, but how are these corners related to the ones downstairs? They did like the first 2 entries give you the entries of the corners downstairs, because this is like X and Y, X1 and X2. So if you just keep track of the first 2 entries of each vector, that corresponds to the points on the XY plane where the corners are situated. Because this live in 5 dimensions, right? So it's kind of like the shadow, what you would call like the projection in linear algebra onto the XY plane. That is what maps into like the corner. So for example, if you look at the first 2 entries here, that's kind of easy, like the 0, 0. So that kind of is the one that projects to the origin, and like 0, 3 halves is like, like you kind of can do it like on GeoGebra. If you go to GeoGebra, you'll see like how these like numbers. Oh, actually, I can put them side by side, I think, at least for you, like here. So for example, what this is 3 halves, 1 half, which is 1.5.5. So 1.5.5, this is like the corner A, and then like like 3 halves, 0, 3 halves, 0 is 0.5, 1.5 zeros. Well, 1.50 is here. And then like, for example, 0, 0, well, is here. And so you see, like, if you look at the first 2 entries of like each vector, that gives you like the corresponding corners in the, in this.
Those 3 equations, if we did like slack variables and then all the stuff after, that's how we got.
Right. Yeah. But it's kind of like, so it's kind of like, see, could do, because like, like the 5D picture cannot be really understood so well, but at least in this case, like, like you kind of see that matches. Okay. So this is like a very thorough example, of course, like longer than like I would ever give you in practice, but it's still kind of like nice to see all of that in detail. Now there's this thing about degenerate solutions, which is like the last topic for the exam, which I'll mention, which is like a very simple definition. Okay. So like, what is a degenerate basic solution? It is, let me see if I have like an example here. Where do I have it? Okay, so it is a basic solution. It is a basic solution to AX equals B, when at least one of the basic variables happens to be 0. So if you remember how we found like if you remember how we found the solutions, right? After we found the basic variables, right? After we found the basic variables, we would set equal to 0 all the others. What I'm saying is that for a degenerate solution, one of the original ones that you were finding ends up being 0. So like, like you kind of have more zeros than you would expect, like in a sense. So like I'll show you. Let me show you with a picture. I'll kind of go backwards this time. I'll start with the actual inequalities, build the matrix, because it's easier to see what like the degeneracy is coming geometrically, and that's the last thing I'll explain today. So here's an example of what is like a degenerate solution. So imagine I had given you minus like x1 plus x2 greater, something very simple. X1 greater or equal to x2, and then that x1 is greater or equal to 0, and x2 is greater or equal to 0. So there are only 2, in fact, since there are only 2 inequalities, I can kind of like, I'll just draw them like, okay. So this is x1 and x2. So x1 less or equal to 2, like you just put like the number 2 here, right? And then x1 minus x1 plus x2 like you set it equal to 0, so you get x1 equals x2. Okay, and this gives you the point 2, comma 2. This is like 0, comma 0. And then this is 2, comma 0. Okay, so this is kind of more like a realistic example of like the type of thing that I would give you, because this doesn't take too much time to do everything explicitly, you know, if you wanted to do it. So the polygon in this case is like a triangle. Okay. And okay, and so it has 3 corners, as you can see. And so if you wanted to set this in, because there are 2 inequalities, right? If there are because there are 2 inequalities, you have to add like a slack variable for each of them. So you would have something like minus x1 plus x2 plus x3 equals 0. And then you would have like x1 plus x4 equals 0. So that is like the equational form of the system. So as a matrix, it's like a 2 by 4 matrix. So it's negative 1, 1, 1, 0, and then 1, 0, 0, 1. Okay.
Professor?
Yeah.
When we add slack variables, do the slack variables also have to be greater than or equal?
Right. Sorry, I forgot to write that explicitly, but yeah, all of them become non-negative. Yeah.
Sounds-
That's why it's kind of chosen this way. Yeah. So that everything is always non-negative, whether they're original variables or slack variables.
Okay,
Yeah.
sounds good.
Yeah. No, but thanks for like bringing that up. So that's the matrix A, and the vector B would be like, you know, two, 0, 2, right? Two. I'm sorry, I should like it should have been a 2 in this last one. Sorry about that. Please fix that. This is A, this is X, and this is B. Is that okay? Everyone with me so far, so good? Uh, okay, so, and now, of course, I won't go through all of this again. I'll just show you like a degenerate solution for this system. But the idea is like, if you were to find out the basis, right? Like now, because this is 2 by 4, you have to find the 2 by 2 matrices here, which is way faster, right? Like this doesn't have like as many options as before. But for example, what is that obvious? And this will happen a lot in the simplex method, that sometimes there's like an obvious basis here. The obvious basis is like the last 2 columns, because that corresponds to the identity matrix. So like kind of like the most natural basis like to start with would be like the basis like 3, 4. The corresponding basis is just like the identity, right? And then the solution, like you would need to solve like AB times XB equals 0, 2, which would be like 1, 0, 0, 1. What is XB would be X3, X4 equals 0, 2. Okay, it is identity matrix. It does nothing. So you can read off literally what the values for the, you know, what the values for the variables are. So that gives you that X3 equals 0. Like I'll put that, like that is kind of like the important thing, that you get X3 equals 0 here, and that X4 equals 2. Okay. So this is like a basic variable, which is 0. So that is what makes it degenerate, basic variable. So like the corresponding solution, which would be like you have to put like 0 in positions 1 and 2, but now you have like a 0 in positions 3 and a 2 in the last position. That would be a degenerate basic solution. Okay. Is that making sense? And I will explain geometrically what's going on. Like there's like a geometry of what's happening, but more algebraically, one way to think about a degenerate solution, like, okay, it is that it has a zero, but the thing is that it has more than one basis that produces it. Like, that's another way to understand that degeneracy. So for example, if you had taken, and if you take also taking, if you had taken the basis 2, 4, right? If you take 2, 4, what if you take two columns 2 and 4? It is the same matrix, right? It's still like the identity matrix, right? Like the identity you get also like the identity matrix. So of course so like in this case, like you would then find like, for 2, 4 that x2 has to be 0 because like nothing has changed. So it would be that x2 has to be 0 and x4 has to be 0 here. So in this case, like the solution would be 0, 0, 2. Okay, which is the same as the vector from before. So for a degenerate solution, there are multiple bases that can produce it. That's what's going on here. Like degenerate solution, more than one basis produces it. Okay, that making sense? Because like usually, like like there was like the original basis, like the basis I started with, which was 3, 4, gave me that vector 0, 0, 2, but this other basis 2, 4 gave me the same vector 0, 0, 2. So that same vector 0, 0, 2 can be obtained in more than one way. Yeah. Oh yeah, sorry. Thank you. Like, thanks for catching that. Thank you. Thank you. I wrote it well at the end, but not like in the middle. Yeah, thanks a lot. Perfect. But okay, this is all very algebraic. So what is happening geometrically? So geometrically, what's happening, just to go back to this picture, geometrically, again, like how, like these vectors are all in 4 dimensions, right? But what I was telling you is that if you want to see to what corner that matches, you just look at the first 2 entries because those are x1 and x2. So geometrically, this corresponds to the origin. So what that is saying is that the origin is at the degenerate solution. So like or like a degenerate corner. So this is like and I'm almost done. I just need 2 more minutes. So the corner is degenerate. Okay, because again, you keep track to these 2 first entries. So like the corner is degenerate. And the reason why that's happening is because this particular corner, it is in this picture is the intersection of 3 lines. Okay, so the corner in this case, when you have two, like 2 lines intersect at a point, right? So when you have 2 lines, the intersection is a point. It is very when you have 3 lines, it is kind of like a big coincidence for the 3 lines to exactly pass through the exact same point. So what are the 3 lines here? The first line is like the hypotenuse that you see here. The second line is the oops, sorry about that. The x-axis. Remember that the x-axis is a constraint because like the variables have to be non-negative. And the third line is the y-axis. So what makes, like, if you look at the other 2 corners, the other 2 corners are only intersections of 2 lines. So for example, this corner is just like the intersection of the green and the red, and this corner is only the intersection of the purple and the red. So these other 2 will not be degenerate. What makes this one degenerate is that it happens to be the intersection, the 3 lines happen to pass through it. When in general, you should only expect that to happen for like, with 2. So there are kind of more lines that pass through it than what you would expect. So it's because 3 lines pass through it. 3 lines instead of 2.
So if it's more than 3 lines,
More than 2.
then 2 lines, it's degenerate.
Right, 3 or more. Right. So if 3 or more lines meet at the same point, it would be degenerate. Yeah.
Is that a bad thing?
Well, it can make the algorithm break down. Yeah. So like that's why you'll see it once we kind of work on the specifics of how the algorithm works. Um, because pass through pass through the origin. Yeah. So like, no, like we definitely are singling out because it can be something you have to look for. But there's like a standard solution to fix it, but it's a clever solution, but I'll explain it once we get to the algorithm method. Okay, so let's finish here. So this is like the last topic for the exam where like, I would ask you maybe to identify if any of the solutions that you found are degenerate or not. So you just have to check, did I get a 0 as one of the basics variables? Okay, so let's end here. And again, if for whatever reason we have a snow day, I'll just let you know. And then on Wednesday, we would meet online, but hopefully that doesn't happen.
Professor.
Mhm.
So I read the